Hello and welcome to Ready to Derive. Thus far in the calculus series, we have learned all about limits, the first of the two integral pillars of calculus. In this video, we will explore the second of those pillars, continuity, the definition of which is intimately tied to the concept of a limit. That a function be continuous is an essential precondition to many, if not most, of the techniques and methods that we will learn moving forward. As always, there will be lots of practice problems and accompanying visuals to help make the concepts concrete. Without further ado, let's get started. So before we dive into the definition of continuity, let's just get sort of a better conceptual understanding. So to do that, I've set up these three condition statements. So this first statement is f of a is defined. Second statement is the limit as x approaches a of f exists. And statement 3 is that if 1 and 2 both exist, they're equal. So we're going to make a sketch for each of the following scenarios. So condition 1 is true, but not 2. So we are, first of all, looking at this one. Condition 1 is true, but not 2. And obviously that would imply 3 doesn't hold, because if 2 doesn't exist. So condition 1 of true is true, but not 2. And f of a is defined. So let's make a little sketch of that. You can pause the video and try it yourself first. But f of a is defined, so let's think. We need to have a point here that exists, but the limit mustn't exist. So I need to, let's see, if I came in from here, I need to depart to the right somewhere else. So this would be a situation in which this is true. And now let's go to the second one. Condition 2 is true, but not 1. So the limit exists. So let's set up at a, the limit exists. So I know I have to have something looking like that, but f of a is not defined, right? So condition 1 is not true. So I've got something going on like that. All right, let's go here. Conditions 1 and 2 are true, but not 3. So I'm going to start off with, I know the limit exists. So I've got to have something like this. And I know f of a is defined, but it can't be equal to the limit. So I'm going to put it up here. And then finally, we come to here where all conditions are true. So let me set it up as in the previous one. So I know the limit exists, right? And I know f of a is defined, but they're actually both equal. So therefore, I'm just going to fill in this little hole here. And what we've constructed in this last case here, this one here, I hope you've got the sense that this function is said to be continuous at x equals a. And because the holes, there are no holes, there are no gaps. In none of these have I drawn an asymptote, but that could be a problem as well. So continuous at x equals a suggests that there are no interruptions in the graph, no breaks in the graph. In fact, some people say very loosely that you don't have to pick up your pen off the paper to continue drawing the graph. So let's bring our understandings from the previous slide to create the definition of continuity, which says that a function is continuous at x equals a if the limit as x approaches a of f of x is equal to the value of the function at a. So these are the three statements from before. If you remember, this was the right-hand side was statement number 1. The left-hand side is statement number 2. And stating that they are both equal is statement number 3. And if this doesn't hold true, we say that the function is discontinuous at x equals a. So just to reinforce this one more time, if the limit exists at x equals a, you know at least that this much is true. And if f of a is defined and is equal to the limit, you know this is filled in, and hence the function is continuous at x equals a. So let's look at an example. Use the definition of continuity to determine if the function f of x, this piecewise function, is continuous at x equals 2. So let's recall the definition of continuity from the previous slide. And let's get started. Well, we know there's kind of 3 parts to establishing continuity. So I'll break them down. And the first step is to check that f of a, or in this case, f of 2 exists, and find out what it's equal to. So if x equals 2, we know that we need to use this branch of the function, which means that the y value is -1. So f of 2 exists, and it is equal to -1. The next step would be to see if the limit as x approaches 2 of f of x exists and what it's equal to. And to do this, we really need to evaluate left and right limits because this is a piecewise function. So approaching x equals 2 from the left, we would use this branch. And so we would just plug in 2 squared minus 1 equals 4 minus 1 equals 3. And we're allowed to do that even though it says here that x is less than 2. We're allowed to put x equals 2 in to the function to just determine where the graph is heading, and we acknowledge that there might be an open circle at x equals 2 on this part of this branch. And the limit from the right, then we would use this branch here, and we put x in with 2. -2 plus 5 equals 3. Since the left and right limits match, we can safely say that the limit as x approaches 2 of f of x is 3. But now we have a problem because these do not match. So therefore this function is not continuous at x equals 2. So you could say discontinuous, or not continuous at x equals 2. Let me erase that bit. And if you want to employ the more formal definition, because we just established that the limit as x approaches 2 of f of x is not indeed equal to f with a function evaluated at 2. So let's look at the 3 types of discontinuities that you could come across in a graph. The first is called a removable discontinuity, also previously referred to as if you recall from pre-calculus, we might have called that a hole, also referred to as a point discontinuity. In these discontinuities, what you have going on is that the limit of the function as x approaches a exists, but is not equal to the value of the function at a. It's also possible that that function doesn't even exist at a. So it's possible that f of a doesn't exist. So this would still be a removable discontinuity, even if I took away that f of a value, or f of 2 in this case. It is still the same type of discontinuity, and it's called removable because all it would take would be to redefine the function, to redefine f, in this case f of 2, as 4, and we remove the discontinuity and make it then continuous there. So that's why it's referred to as a removable discontinuity. The next type is called a jump discontinuity. And in this case, f of a could exist. It's possible, it doesn't have to, but the key here is that the limit doesn't exist. All right, let me stay with white. So the limit as x approaches a from the left does not equal the limit as x approaches a from the right. And the last type is called an infinite discontinuity. And this is a case where one or both branches, or presence of a vertical asymptote, obviously, and one or both branches are going to positive or negative infinity. So, and it could be from the left or right. So I'm going to put limit as x approaches a from the plus or minus from the left of right of a, could be plus or minus infinity. They don't both have to be infinity, but one of them has to for an infinite discontinuity to exist. So let's look at an example. We are to identify the discontinuities of f of x, this piecewise function again by type. So the 3 types we just looked at in the previous slide. You might suspect that all we really need to look at, that x equals 0 could be a potential discontinuity, but also we need to be exploring the actual functions themselves, the branches, to see, is there a discontinuity hidden in there that's sort of not obvious, that we have to analyze? And because they're both rational functions, potentially there are. So here's a couple of fun facts. I'm not sure if they're fun, but they're definitely facts. If f and g are continuous at a, then the following functions are also continuous at a. And it's sort of stating the obvious, but it's helpful when analyzing these type of functions. So we definitely are in this category f over g over here, but it's good for you to kind of have these in your notes for future reference. And then one other sort of obvious fact, the following functions are continuous at every number in their domain. Polynomials, rational, that's what we have, looks like we have going on here, root, trigonometric, exponential, and logarithmic. So with those facts, we will proceed to the next slide to analyze this function. So let's bring up that function, piecewise function from the previous slide, and we're going to analyze the presence of discontinuities in this function. But the fact that I would like to recall is that if p is continuous and q is continuous, then the quotient p over q will also be continuous as long as q is not equal to 0. And this will be important as we do have the presence of rational functions within this piecewise function. So I always like to start with the obvious candidate for discontinuity, which is where the piecewise function changes definition. So let's have a look at the limit of this function as x approaches 0 from the left. In this case, we will be using this branch, substituting into here, and we get 1 over 0 plus 1, which equals 1. And if we are interested in the limit as x approaches 0 from the right, that's when x is greater than 0, so we're going to plug x equals 0 in here. I'll leave that for you to do, but it comes out to 1 over negative 1, or just negative 1. And because the left and right limits exist but are not equal, we know that we have the presence of a jump discontinuity at x equals 0. So let's go in and explore the individual branches of this function. So y equals 1 over x plus 1. So think of this as p and q. And p and q are both linear functions. The second fact says that those are continuous across their domain. And the domain of a linear function is negative infinity to infinity. So the p over q will be continuous everywhere, as long as x plus 1 is not equal to 0, which means x must not be equal to negative 1. So we obviously want to find out what's going on at negative 1. If you plug negative 1 in, you would get 1 over 0, undefined, so we know there's some infinity related business going on here. So let's just work out a limit at infinity. Let's see what would happen if we approach negative 1 from the right. So to think about this, it's just good to maybe plug in a value that's very close to negative 1 from the right. That would be like negative 0.9999, say, plus 1. And this is tending to 1 over, that's getting very close to 0 on the denominator, but it's always going to have a positive charge. No matter how close you approach from that direction, 0, the negative 0.999, keep on going, plus 1 is always going to be slightly positive, very close to 0. And we know from a previous video that this therefore is heading to positive infinity. So we can say the limit as x approaches negative 1, from the right is positive infinity. And we don't even have to check from the left. The minute we have an infinite limit of that sort, we know we have an infinite discontinuity at x equals negative 1. And now we are going to, let's go in and have a look at this function here. So y equals x squared minus 2x plus 1 over x minus 1. Again, this is p, this is q. P is quadratic, q is linear. The second fact, once again, says that quadratics and linear functions, continuous over their domain, they both share the domain of negative infinity to infinity. So p over q will be continuous everywhere except when the denominator is equal to 0. And that would give us that we can't have x equal to 1. So now we're going to employ a limit strategy from a previous video about evaluating limits algebraically. And we have the tools now to be able to work out the limit as x approaches 1. If we just factor the numerator, we see that we actually can cancel out the problem value. The problem value is x equals 1. And if you notice, we're sort of removing the problem. So that's a spoiler alert that a removable discontinuity is coming up. And we're at a place where we can just plug in x equals 1. So plug in x equals 1 into this part here that's remaining. We get 1 minus 1 equals 0. So we know that the limit exists. We know that the function is undefined at x equals 1. From up here, we discovered that obviously x cannot equal 1. So therefore, we have the presence of a removable discontinuity at x equals 1. So all three discontinuities appear in this function, and in the next slide, we'll take a look at the graph. So here's the graph of the piecewise function from the previous example, and I just want to point out the discontinuities that we discovered from before. So at x equals -1, we have an infinite discontinuity because there's a vertical asymptote there. At x equals 0, we have a jump discontinuity. And at x equals 1, we have the removable discontinuity, also known as a point discontinuity, or formerly known as a hole, and we'll probably still refer to it as a hole moving forward. So I want to segue using this graph into one last definition, a couple of definitions you need to know about continuity, a little more nuanced take on continuity, and it's about whether a function is continuous from the left or right. So if a function is continuous from the left at x equals a, if the limit as x approaches a from the left of the function actually equals the value of the function at a. And the same is true from the right. Is the limit from the right equal to the function, the value of the function at a? And now this does not apply to, say, a value like x equals 2, because the function is continuous at x equals 2. There's no need to distinguish from the left or right. It's more important that the function is just continuous. So where this is helpful, though, is at points of discontinuity to talk about continuity from the left or right. So let's take at x equals 0. So at x equals 0, and let's look at the limit from the left and right here and see how they compare. So from the left of 0, let's just hop on the curve and jump on the curve and have our x value approach 0, and we seem to be approaching the value of 1. And from the right of 0 plus, let's hop on the curve just to the right, and as our x value approaches 0, we seem to be approaching -1. And now we need to see which one of these, if either of them do, matches the value of the function at 0. And the value of the function at 0 is really just which, at x equals 0, where is a point that has a y-coordinate that's a real number. Here we go, -1. So f of 0 is equal to -1. And because it's these two values that match, we can say that this function is continuous from the right at x equals 0, but not from the left. And just for another point of comparison, for example, at this discontinuity, x equals 1, clearly it's neither continuous from the right or left. And so one last detail, this defining continuity from the left or right also allows us to say whether a function is continuous over a closed interval. Now over an open interval, it's pretty obvious, it's safe to say, for example, that f of x is continuous over, and let's just take one interval, use a different color here. I could look at this portion of the curve that I'm kind of highlighting here from -1. It's heading up to infinity there, but from -1, as long as I keep that open to 0, I can say that f of x is continuous over that interval. But now that I've introduced continuity from the left and the right, I can also define a closed interval. So let's come and look at from here to say 0.5. So from 0 to 0.5, I can also say that it's continuous from 0 to 0.5 because I know at 0, with a closed interval, I know at 0 it's continuous from the right, and I definitely know at 0.5 it's just continuous. So this introducing this definition of continuous from the left and the right allows me to define continuity over closed intervals, which will be helpful later on in the course. So before we end, one last question. Informally, can you just define a continuous function to be one for which you don't have to lift your pen while drawing? I'm going to call up a function we met in the very first video on Introduction to Limits. And you can go back to that first video to see this function and in greater depth, but we graphed it. I'll show a graph shortly, but if you think about it, so if x is a rational number, so let's take a rational number like 1, then the y value just matches x. So 1, 1. Say x is negative 2/3, negative 2/3, etc., etc. And then 0, 0. That's an important one. And if x is irrational, the answer is always 0. So that would be root 2, 0, negative pi, 0, etc. And if you try to imagine what that graph looks like, you could try and visualize it, maybe pause the video and visualize it before I show it to you. And here it is. We have basically kind of two sets of points here. We have points that lie along y equals x. Those are the points whose x values are rational numbers. And then we have a whole bunch of points that lie along y equals 0, and those are all points whose x values are irrational. And we showed in that first video that the limit as x approaches 0 of this function is indeed 0. And just to give you sort of a quick review of that, it's clear that any irrational number, so as you get, doesn't matter where it is, but especially as you get closer to 0, any irrational number will output a y value of 0. So in order to establish that the limit is 0, then we have to worry more about the rational numbers. But all you'd have to do is take a really small rational number like 1 times 10 to the minus 51, and that will output an answer, a y value of the same to the negative 51, which is very tiny, almost 0. And if you made that instead of negative 51 to the power of negative 1,000, you would deliver a y value that's even closer to 0. So it's safe to say that the limit as x goes to 0 of this interesting function is indeed 0. Well, if we go back up here and look at the point 0, 0 is on this function, then we also know that h of 0 equals 0. And since these two match, these two values match, we know that the limit as x goes to 0 of h of x is equal to h of 0, which means that h is continuous at 0. Which kind of might come as a surprise, because in order to really accurately graph this function, you have to keep lifting your pen off the paper in order to plot the next point. So here, this is why the definition of continuity is so important, that this is the definition of continuity, and not that you don't have to lift your pen off the paper while drawing. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.